Hey guys, welcome to today's lecture. We're going over the basics of game theory and some strategies. Let's get straight into it. Alright, so what exactly is game theory? Well, I'm going to give you the most academic definition in the world, and then I'll try to break it down. So first, game theory is the study of ways in which interacting choices of economic agents produce outcomes with respect to the preferences or utilities of those agents, where the outcomes in question might have intended by none of the agents. Essentially, what this is saying is, game theory is the study of a game in which your decision as an economic agent depends on the decision made by the other player or economic agent. It is a series of these interacting choices that create the outcomes of the games. And while neither player is intending for one certain option, because the other player might have made that decision, then you both would end up with that secondary decision or secondary outcome. And these are based on the preferences, utility of the previous game. If you remember from last lecture, that's where we talked about our utility and our preferences. But in this case, it's quite simple. It's really just the inherent biases and values that we put onto the players. So to give this more concrete situation, we'll give an example, and this is going to be the first example that you're going to learn in every single game theory course. Even political science majors learn this. I know. So, an example is the prisoner's dilemma. Let's scoot over my webcam. I don't think I have a ton of stuff in the bottom left. We need to make a couple assumptions about what we're about to lay down here. Actually, we'll start with the story first. Two prisoners. Two people convicted of a crime are being interrogated by the police. Each one of them is told that they either confess, and if they confess, then they'll get let off with less of a crime than if they don't confess. Or that their buddy they have evidence, and they're going to go in prison, but if they confess, they'll be given lesser sentence. What this means concretely is both these prisoners are going to be locked in separate rooms, talk to the police individually. They cannot communicate with one another. There is zero coordination. They both make their decisions simultaneously, whether they're going to confess or not confess to the crime. And they only run through this once. There is no secondary time where they're going to go through their confessing action again. In very concrete numbers, if player A, or red in this case, is to confess, then they are going to get 3 years. If player B also confesses, if player A is to confess and player B is to not confess, then player A is let off scot-free, 0 years in prison, while player B gets 5. If both players, and then vice versa, if both players are not to confess, then they both get 2 years in prison. Now, you can see that represented in the graph in the right of the screen. And the way that we would read this is the label that is underlined in blue is the outcome that you would get in blue. So the bottom, you would read that from confess. I think you can see my mouse. You would have confess, and that will get you 3 years if other player confesses, or 0 years if the other player plays not confess. Remember, this is a game. We're playing actions. Each of these are players. And so now you should think to yourself, all right, do I confess or do I not confess? Is there even a way to figure out the situation? Is there a way to really concretely say which option is better? And there really is. And we're going to look through that, and it's called the Nash equilibrium. So the first thing that we should do whenever we're trying to find this Nash equilibrium is think to yourself, if you know the other player is going to play confess, what is the best outcome for you? And we can look at our graph, and let's say that we are blue, and we're looking at what would happen if a red plays confess. So first, we look laterally, and we can see that if they play confess, we can play confess and get 3 years, or we can play not confess and get 5 years. So in this case, we'll want to play confess. And then we'll look at what happens if we know that they will play not confess. Well, we can look at and say, if they play not confess, we'll get 0 years if we play confess, and we'll get 2 years if we play not confess. Well, it seems like in both situations, playing confess gets us less years. Yes, it's better for both of us to play not confess, but if they played not confess and we played confess, we'd get lower overall. And so even though for both of us it might be better to play not confess, by the virtue of the fact that they might play not confess pushes us towards playing confess. And it's the exact same for them too, where they can rationalize out that they will always have a better option to play if they were to, they can move to less years in prison if they were to play confess, no matter what the other person does. And so that's how we get something called a Nash equilibrium. And you can see it right here. Underlined is the best option available, and the one that has 2 underlines underneath it is the Nash equilibrium, and I marked it with an X. Now, this is just what happens whenever you play one time. You decide that's the point that we're going to get at. What happens if you play multiple times? Well, eventually it's possible that you might move to 2 years and 2 years, both playing not confess. And that's very interesting. The fact that this game might be played multiple times with 0 coordination between players, that this equilibrium would shift over to one that is less years for both players. Now, how is that possible? Well, we'll have to look at the strategies that are possible and generally what are associated with some of these game theory decisions. Now, these 3 strategies, we can call them altruistic, selfish, and then there's a third category, which is dynamic. So first we'll go with the unchanging ones. This is something that they will play every single time. The altruistic position is one that will always play not confess, no matter the situation. You can play confess to them 80 trillion times in a row, and the next time they're going to play not confess. This is pretty easy to game, where if you're going to just play confess every time, you're going to continue to get 0 years. The other option is selfish. This person will always play confess. Now, once you always play confess, then, well, if the other person's always going to play not confess, then you're in a pretty good situation. If the other person, it's honestly, that's the point which we would get in our one play game. But remember, we're playing multiple, many times over a long period. And that comes with what happens if you have a changing dynamic strategy. Now, this one's going to be called tit for tat. What that means is if you play something, you cheat or you confess or you play the bad option, then tit for tat will play the bad option one time for every single time that the other person has played that. What that means concretely is if you were to play altruistically, then they would play altruistically as well. If you were to play selfishly, then they would play selfishly as well. If you were to play selfishly, switch your strategy to altruistic, then they would follow in suit. In fact, we can map out these different strategies against each other and see what outcomes occur. For example, I kind of already went through this, but we'll do something just so you get the graphs in your head. Altruistic versus altruistic, they'll both end up playing not confess and get 2 years every single time. Selfish versus selfish, they'll play confess every single time. That follows our Nash equilibrium, but not for multiple games, but they'll end up with 3 years every single time. And then, once we have changing strategies, we end up with selfish versus altruistic. With this, then it will always be confess, not confess. So selfish will always get 0 years, while altruistic will always get 5. But then we get dynamic strategies. So tit for tat, they're going to play confess, and the other person's going to play confess. So it's almost as if it's selfish and selfish. Same thing for tit for tat and altruistic. It's almost as if, ignore the cursor that's supposed to be on 2 and 2, my mistake. Actually, sorry, that is not, ignore what I just said. Tit for tat has the ability, if they play confess first, then they will never have to change because it's dynamic. They have never received a penalty for playing this option. And so against an altruistic player, they have the capability of gaming the system, essentially. And so the difference between a selfish and an altruistic, the difference between a selfish and a tit for tat is that the tit for tat is capable of playing against a selfish and maximizing their outcome, and against an altruistic and maximizing their income. The least amount of years in prison, or minimizing it. And what's most important is they're capable of playing against themselves and going down to not confess. This is going to be the core of a lot of multiple play game theory situations, where they're actually capable of moving dynamically to the correct situation at the given time. Because globally, or universally for all parties, all society involved, both players playing not confess is the thing that gives us the least amount of years total. And so a dynamic situation is the one thing that allows us to move towards that situation. Because if you look up and you add the numbers and confess, it's 6, and then 5, but this is the only one that goes to 4. And so it's this dynamic situation that allows for actual movements towards equilibrium. Societally maximizing positive equilibrium. And equilibrium is just the means that both players are pushing towards to meet. It's just the staying point of once they reach it, they will always reach it. Now, these games are under assumption that they will play forever. This always isn't the case. Sometimes players are only going to be playing 2 games, 4 games, 5 games. Sometimes they play only this certain amount. And that also changes strategy. All these different tiny factors are going to change your equilibriums that you might find in tit for tat. This is the easiest, and frankly, it's the most well-known game theory, but if you enjoy a little bit of this, then perhaps we can move towards further complex situations. But remember, as within the previous lecture, these tiny interactions multiplied across thousands and thousands and thousands make up the totality of human interactions. Even if they're not specifically playing this one game, you change the variables slightly, you change people's preferences, you change the economic actors and the strategies, then you end up with really what can be called the essence of human action or the economy. Thank you for lecture 2.